Okay, welcome to the video tutorial. This is the tutorial number 4. Okay, we will start with the part A. Here is the first question. Why, when we have a pyrrole, we treated the pyrrole with methyl iodide, why we don't get the methylation in the pyrrole? Well, the reason is quite simple. Remember that pyrrole is an aromatic, and the paraphylelectrons of the pyrrole, of the nitrogen of the pyrrole, are part of the aromatic system. That means they are not accessible, they are not nucleophile. For this reason, when we add methyl iodide, this reaction will not work. How we can make this work? Basically, if we add a base, why a base? For example, sodium hydride or butyllithium, okay? First of all, we remove the proton with a protonate, and now we have here a paraphylelectron that is a negative charge that can react with the methyl iodide, obtaining the final compound. Okay? We require a base to deprotonate this and make the nitrogen nucleophile, because the paraphylelectrons of the nitrogen are part of the aromatic system. Okay, clear? We go for the second question of the part A. We have this reaction. We have a furan, okay? We have this functional group in the furan, and the first that we have to analyze is what is doing this functional group. Okay, this functional group is an electron donating group. Okay, this is adding electron density to the ring, making the ring more electron rich. Okay, I know that the oxygen is more electronegative than the carbon, but the important is that the paraphylelectrons of the oxygen can make resonance with the aromatic ring. And what we are doing, this is typically an Friedel-Crafts reaction, remember, because the pyrrole is more electron rich than not benzene. What is happening here is that we don't need to use the strong conditions of benzene, we don't need to use acetyl chloride. With acetic anhydride it's more than enough, and even we can use a soft Lewis acid like indium chloride instead of the normal aluminium trichloride. But basically this is an electrophilic aromatic substitution. Okay? And remember, electrophilic aromatic substitution is a reaction that is favorable with electron-rich rings, like this. Then, what we have to notice to know the regiochemistry of this reaction? Well, where is orientating each group? We know, only for the fact that this is a furan, this will orientate to the C2 positions. Remember that is the same than pyrrole. This will orientate the two C2 positions. Okay, and then we have to analyze what is doing this group. It's an etoxide. We said a few seconds ago that is an electron donating group. That means if it's an electron donating group, we'll activate the positions ortho, para. And remember, ortho, meta. Okay? Remember that when we are trying to find the position for a group, for a functional group, we have to go through the carbon, ortho, meta, ortho. We cannot go through the heterocycle. That's not possible. It's not how it works. Then we know that this etoxide is activating this position and this position. That means that the only position that is double activated is this. That means that the reaction that will take place will be this. Okay? With the addition of the ketone in the second position near to the etoxide. Always when we are facing this type of exercise, what we have to do is to see which is the position that have more favorable interactions. I mean, what is the position that is more activated for the different functional group or range that we have. Second example, here is different. What we are doing is we are adding a sodium methoxide. Sodium methoxide could be a base, but also is a very good nucleophile. This is a nucleophile. That means what we are doing a nucleophilic substitution, aromatic substitution, nucleophilic aromatic substitution. Okay? This type of reactions is not working well with electron-rich rings like pyrrole. This is why, if we want to do this reaction, this pyrrole first of all has to have a good leaving group, fluoride, okay, and a very good activating group. That means we need a group that is electron withdrawing. Even in these conditions, the reaction will not be good, but okay, could work. Okay, what is happening is the methoxide is attacking the atom that has the halogen, the fluorine. Remember that here the best group is a fluorine because it's very electronegative and it's very small. Okay? And what is happening is, after addition, elimination of the fluorine, and the final compound will be this one. Okay? And remember, in these conditions, the nitro group is activating ortho-para again. Ortho-meta-para. That means that the fluorine has to be or in this position or in this position. Will never be in this position. Or if it's in this position, will simply doesn't work. Okay, then we go for the third one. The third one basically is telling us which reaction will be faster. Okay, we have here, we are treating a pyrrole or a benzene with the same conditions, acetic anhydride and a Lewis acid, and what we get is the addition of ketone in this position, in C2, okay, that is the active position of the pyrrole, or in the benzene ring. Which reaction will be faster and why? Okay, first of all, we have to know which reaction we are doing. We are doing a electrophilic aromatic substitution. And what we need in order that the electrophilic aromatic substitution will work well? Well, what we need is an electron-rich ring. This ring is more electron-rich than not the benzene. Why? Because here we have 6 electrons, only 5 atoms. That means that we have 1.2 atoms more or less in each carbon. That means that this is an electron-rich ring, this is a normal ring, a zero base, it's benzene. That means that this is the reason why this will work faster. Then, the other thing that we are studying is we have this compound. And we have this reaction. Okay? Again, what we need we need to know which reaction we are doing. In this case, what we are doing is a nucleophilic aromatic substitution. Okay? The methoxide is a base, but also is a good nucleophile. That means this is what we are doing, and what we need in order that a nucleophilic aromatic substitution is working well. Well, what we need is an electron pool ring. This ring, for nature, is electron rich. This is a benzene ring, but we have an electron withdrawing group. That means this is electron pool ring. Because it's electron pool ring, will facilitate the intermediate that is a negative charge in the ring. That means this is the reason, because this ring, aromatic ring, is more electron poor than not this, that this will be faster. Okay? Good. Okay, then we will do the part B. The part B, basically, what we are doing is we are starting with this one for diketone, and we add benzylamine. Okay? Well, basically, a 1,4 diketone is an Pal-Nor synthesis of pyrroles. Okay? How is it starting? Normally this is with a slightly acidic. That means that we protonate one of the carbonyl groups, and the pair of electrons of the nitrogen attacks here to form, in a first stage, the hemiaminal that we protonate again to make a very good leaving group, and then simply we are forming water that is a very good leaving group, and we are forming the iminium, and we get the first iminium. Okay? This iminium, tautomerization, iminium-enamine, to form this intermediate, this enamine, and again, second addition to our carbonyl that previously we activate with a proton. The pair of electrons of the nitrogen will attack here, and what we get is, in a first instance, like before, we have the hemiaminal, we have the hemiaminal, and then we protonate this to do the elimination, and here you can eliminate or well forming the imine or well directly with these hydrogens. Okay, water is a very good leaving group, and what we get is we got the pyrrole at the end. Okay? I do it a little bit fast, okay? But basically this is the intermediate, the key intermediates of the synthesis. First we get the hemiaminal, imine, tautomerization of enamine, hemiaminal, and then elimination to get the final product. Remember that all these steps are in equilibrium. And the only irreversible step is the last, where we are generating the aromaticity. Okay? Good. Then go for the last one, for the second part of B. And this is a typical exercise that I know. Okay. Basically what we are doing here is doing an igration with this compound. Okay? If we are doing an igration, what type of reaction we are doing? We are doing an electrophilic aromatic substitution. This is a electrophilic isn't it? This is an electrophile, the same for all. Then, what we need to know? Well, if it's an electrophilic aromatic substitution, when is working well, electrophilic aromatic substitution? When we have an electron-rich ring. If we have an electron-rich ring, the thing will go well. If we have a less electron-rich, it will go worse. That means we have to choose in which of these different aromatic rings is going the reaction. Okay? First is this. Choose in which ring will happen the reaction. Here we have a pyrrole and a thiophene. Which is more electron rich? Well, the pyrrole. Why? Because the sulfur, you remember that his overlapping with the carbon is quite bad. Why? Because sulfur is by far bigger than not carbon. The difference between the orbitals is so big, that means that overlapping is quite poor. That means this makes this ring more electron rich and more active then. That means that the nitro group, because what we are doing is adding a nitro, will come to this ring. Once we decided the ring, what we need to do is decide in which position of the ring. Because it's a pyrrole, okay, the pyrrole will activate the positions C2 regarding the pyrrole. And then here what we have an electron with rubbing group. Electron with rubbing group, remember, are unactivating, they are not activating, are deactivating groups, but the orientation is meta, okay? Ortho, meta, ortho. Remember, we start counting from the group, ortho, meta, ortho. And always through the carbons, never through the heteroatom, never. That means if we do this, the orientation is this position. That means this C2 position has the activation of the amino, of the pyrrole, and of the ketone. That means that the final product will be, the reaction will take place in this ring and will take place in this position. Okay? Easy. Here we will apply exactly the same. Which ring is more active? Remember, is more active the pyrrole. Why? Because the pyrrole The nitrogen is less electronegative than the oxygen. The oxygen is trying to attract more the electronic density, making the ring slightly more electron poor than not this. This is the reason. Then we know that the nitro will go here. Now, next step, in which position? Okay? We know that the pyrrole is activating the C2 positions. Okay? And then we have this substituent. This is an alkyl group. An alkyl group is an electron donating group. It's not very electron donating, but acts as electron donating. That means ortho para. Ortho, meta, ortho. That means in this position, we will have the activation of the pyrrole plus the activation of the alkyl group. That means that if we draw a final product, we know that the migration will take place in this ring and in this position that is activated for the pyrrole and for the outer group. Okay? Check the difference between this example and this example. Here, this orientates meta, for this we choose this. Here orientates ortho, for this we choose this. Okay, and the last one. Here, it's easier, we have a benzene ring and a thiophene. We know that the thiophene is an electron rich. Why? Because it's a 5-member ring. It's a 5-member heteroaromatic ring. That means that this is the more active. The nitro will take place here, will take place in this ring, and now we have to decide in which position. Sulfur, basically, is a thiophene, will activate the C2 positions of both. Okay, and then we have, like in the first example, electron with grabbing group, a ketone. That means we'll orientate meta. And again, ortho meta, ortho, remember, we start counting from the functional group, ortho meta, ortho, and we never go through the heteroatom, never, always only through the carbons. That means that this position has the double activation. This is where will take place. Alright? Well, this is all of the tutorial. Please remember how we do this when we have two different rings where we can have the reaction. We have to choose in which ring is more possible this reaction. That means which ring is more activated. And then we choose which position will take the reaction. Okay? And that's all. Thank you for your attention and see you in the next tutorial.